Let's get back to work. So we're doing complex analysis and we're developing a whole bunch of theoretical results about power series, including the ratio test and the Cauchy-Hadamard test that detects the radius of convergence. And we're going to start working a lot with power series. But before we can really get into the computations with power series, we need to have some results that reassure us that we can manipulate series in the way that we expect. So we need to have the power to add series by simply adding their terms, to multiply series by following the natural rules. And when we get to power series, we need to be able to differentiate power series by differentiating them term by term. And we need to have some reassurance that that's really going to work. So we're not going to be differentiating series in this video. What we're going to be doing is, instead of looking at power series, we're going to be looking at simple series of complex numbers. That is, these are not functions of z. These are simply infinite series of complex numbers. And we're going to prove some basic properties of these series. So this theorem states three. The first is so easy we won't do it. We'll prove the second, and then we'll prove the third. The third is by far the hardest of them. What we're really doing here is we're reassuring ourselves that addition of series and multiplication of series works the way we would hope that it would. So how would you hope that it would work? If you have a series an that converges to A and a series bn that converges to B, and if you added the series an to produce the series n equals 0 to infinity an plus bn, then you would hope that it converges to A plus B. And so that's the content of this thing. If you take one of the series and multiply it by a constant k, then it would converge to Ka. And then we have this very technical statement on 3. We're going to talk about the meaning of this statement in detail before we prove it. But what we're going to do first is we're going to sort of dispense with 1 and 2, and then the rest of the video will be mostly focused on property 3 here. So 1 is so easy that I'm going to skip it, but I want to show you how property 2 plays out. And the key thing that you need to remember here is the definition of a series. If we have an infinite series, which is a summation from n to infinity, then that, by definition, is the limit as cap n approaches infinity of the partial sum n equals 0 to cap n of a sub n. So this definition of an infinite series helps us to convert an infinite series to a finite series, which is nothing more than a sum, ordinary arithmetic, together with a limit as the length of that sum goes to infinity. So all the properties that we will deduce about infinite series ultimately come from properties of the finite summation and properties of the limit. So let's prove property 2 here, and we'll see that this is really not very hard at all. So proof of 2. So this series, the sum n equals 0 to infinity of an plus bn, is by definition equal to the limit as cap n approaches infinity of the finite summation n equals 0 to cap n of an plus bn. Now, this finite summation can be reordered as much as we like, right? Infinite summations can be reordered, but that's a somewhat dangerous operation, and we have to always be careful of the right hypotheses. Finite sums can be reordered as much as we like. So that means that we can rearrange that finite sum and make it the sum of two finite sums, namely this one and this one, the two partial sums of the A series and the B series. So that's the limit there of a sum. And now we have a limit of a sum, so the limit passes across the sum because the summation operation is continuous. And so we get the limit as n approaches infinity of the finite summation an plus the limit as n approaches infinity of the finite summation bn. And that is nothing more than a plus b. So essentially, we've passed an infinite sum, this operation, across a plus. And in doing so, all we really did was we passed a finite sum across a plus, and we passed a limit across a plus, because those are the properties of the finite sum and the limit. And so when combined, that gives us the same property for the infinite sum. So that's our proof of 2. It's not too hard. The proof of 1 is even easier, and it might make a good exercise for the student. Let's turn our attention to statement 3, which is much more complicated and really warrants a little bit of discussion. So what is going on in statement 3? In statement 3, so before we get to the proof, I want to talk about the meaning of this statement. In statement 3, we are dealing with the product of two series. So I want you to imagine A is the summation of all the ANs, and there are infinitely many of them. B is the summation of all the BNs, and there are infinitely many of them. So let's use this graph to kind of help us out. I want you to imagine that we place the AIs across the bottom, and imagine that they're added, right? Because it's a series. And so, so we have this series. And then imagine furthermore that you place the B sub j's placed upwards. Now, if you multiply A times B, you're effectively multiplying the sum of all of the AIs by the sum of all of the BJs. And this will cause a huge distribution. And so A times B, in a sense, well, this is the summation n equals 0 to infinity of AN, not plus, times the summation n equals 0 to infinity of B sub n. And when we combine this, we will effectively get a double sum, I equals 0 to infinity, j equals 0 to infinity of AI bj, a product of every possible pair. But this double sum is not compatible with our definition of an infinite series. For a finite sum, this would be fine. But for an infinite sum, what does this even mean, right? We're taking a limit as something goes to infinity of a finite sum of a limit of a finite sum. And you see all of these limits and things, they will interact with each other in subtle and complicated ways. And so we can't just take for granted that, you know, this thing just distributes and we're just calculating the product of all of these terms, or the sum of all of these individual products. Because the order in which we add up these individual products could very well have a bearing on the final answer, depending on how they converge. If the series is absolutely convergent, then the order won't change. The answer won't change when you rearrange it. But if the series is conditionally convergent, it could, in theory, converge to a different thing when it's reordered. And so figuring out the proper order in which to multiply all these doubly infinitely many terms is really the name of the game here. And that's what 3 is trying to do. It's trying to produce this doubly infinite collection of terms and convert that to a singly infinite sum of terms, which are themselves kind of ordinary. And they're ordinary in the sense that they themselves are finite sums. So that's what Cn is trying to do here. Cn is a certain sum of products of these terms that are represented here. And I think it'll make more sense if I just draw a picture of C4. So C4 is the sum of all 5 of these terms. So C4 is going to be the summation I equals 0 to 4 of AI B sub n, well, 4 minus I, which is equal to A0B4 plus A1B3 plus A2B2 plus A3B1 plus A4B0, which is the sum of these 5 terms. So what C is really doing is it's helping us manage the product of all of these very many terms and helping us organize them into layers. And the layer is basically given by the total amount of subindex here, right? In A sub j, B, in A sub I, B sub j, how much index do we have? I plus j. And C is organizing by how much of that we have, giving us, C sub 4 is giving us all of the products where the index totals 4. And then C5, well, it'll clutter the picture if I next draw C5, but let's draw C7. So C7 will give us all of the AIBJs whose indices total 7, and so it'll give us the sum of the ones represented as those dots in that picture. Now, if we then produce the series of the CNs, what we're doing is we're taking C0, which is this one, C1, C2, C3, C4, which is shown, C5, C6, C7, and we're adding them all up. And you can see that we will effectively include in that summation of all of the CNs every possible AI bj will be included somewhere. In fact, AI bj will be part of the summation that makes up C sub I plus j. So this is a way of organizing these products of pairs AI bj into layers. Now, it's exactly the right way to organize these things into layers if we're thinking about the addition of polynomials or power series, because if we multiply polynomials, then not only do these things organize and keep track of the bookkeeping for us, they also organize these things into layers of the resulting power of x. So for example, if we have a series which is more like a naught plus a1x plus a2x squared plus a3x cubed plus a4x to the fourth, and let's stop there. And then if we have another, which is using the coefficients of the b's, so then what will happen when we multiply these? When we multiply these two polynomials, we'll get every term of this multiplied by every term of this, which will give us, I mean, because I've stopped here, it will give us this box worth of terms. It'll give us these 25 terms when I multiply this sum of 5 by this sum of 5. But if indeed we're managing polynomials here, we really do want these terms sorted by the total amount of subindex, because C4, for example, will be this product of A4 by B0 plus this product plus this product plus this product plus this product, which will tell us exactly what coefficient we should have on the x4, on the x to the fourth of the result. So this is not only a convenient organizational trick to convert the doubly infinite into a singly infinite, but it's also a perfectly appropriate organization if later we're going to use this to multiply polynomials or even infinite power series, and if we want to multiply them and organize the result by the power of x that we get. So that's all to convince you that this is a very natural thing to do. And then if we add up all the CNs, as I mentioned, then we're basically adding up all these off-diagonal layers. Each one of them is perfectly defined because it's not an infinite sum. Each one of them is a finite sum, so no problem. And then we have a singly infinite sum of these ordinary finite sums. And so we can treat this as a kind of a normal infinite sum and not a doubly infinite sum, which would require extra definitions of how we sum things doubly. So that's why we're doing this. And then the idea is if you really do take the series of the Cn and add up all of these things, then it is the same as taking A times B. It is this basically what you would try to do there. So that's what this third statement is all about. And we need to get to a proof of this third statement next. So it's going to be a challenge to fit the proof of this statement onto the amount of space that I have here. So what I'm going to do is I'm going to steal this. I'm going to start the proof here. And by the time I get down here, I'm going to erase the statement. But you have a record because you can always rewind. So the series of ANs converges to A, and the series of BNs converges to B. And so proof of 3. So we'll show that the summation, the infinite series n equals 0 to infinity of Cn is equal to AB. Now, how are we going to show this? We're going to analyze this thing as a limit, and we're going to subtract the nth term minus that, and we're going to show that that's 0. Now, for convenience here, I would like to have some notation for the partial sums of the series A and also of the series B. So let's let AN be, actually, let's make that a cap n. A subscript cap n. Let's let that be the summation from I equals 0 to cap n of A sub I. And similarly, we're going to let B sub cap n be the series j equals 0 to cap n of B sub j. I could just as well use an I index here, but I'm going to, for the purpose of this proof, I'm going to be in the habit of using j indices for B and I indices for A, just so that we can keep ourselves organized. So then what we're going to do is we're going to analyze this thing as a limit. So the summation n equals 0 to infinity of Cn is equal to the limit as cap n goes to infinity of the finite sum of n equals 0 to cap n of c sub n. And so if we're going to show that this limit is equal to ab, then we're going to take this guy and we're going to subtract ab, and we're going to show that that goes to 0. So let's do that next, and then I'll erase this stuff. So consider the summation n equals 0 to n of Cn minus AB. And I'm going to take absolute values of that because I'm going to reason that it's going to be arbitrarily small. And we're going to consider that. And in the context of considering that, we're going to let epsilon be greater than 0. And that the idea of letting epsilon be greater than 0 is I'm going to show that for suitable choice of cap n, this thing can be made less than epsilon. Now, this proof is highly technical, and I always have to review it before I present it because it's not so easy. Before I erase the statement, I want to call your attention to one of the hypotheses of the statement. This proof assumes that the series AN converges absolutely. That might seem strange, and it seems strange to me because the series AN and BN play absolutely identical roles in the hypotheses and the statement, except here we assume that AN converges absolutely. In fact, it would be sufficient to say that either one of them converges absolutely, then it will be fine. Then this will be true. But this theorem is not true if neither one of them converges absolutely, which is strange. So here, the real hypothesis is that one of them converges absolutely, but I'm just, for simplicity, going to assume that the one that converges absolutely is AN. So this is the thing that we need to show is less than epsilon. Now, let's examine what it is. And I'm going to use this picture to examine what we're actually computing here. I'm going to erase this notation for C4, more or less, and then I'm going to look carefully. I'm going to imagine that cap n is 7 here, right? So we have infinitely many terms to manage and think about, but I want you to imagine that cap n is 7. Then this summation n equals 0 to cap n of Cn is actually the summation from 0 to 7. And it's the summation of all of these layers. So effectively what we've got there is, in red, this thing is actually equal to this summation of these however many terms. I think it's 36. So, so this in red corresponds to this summation. And then A times B, well, I'm not going to draw that on the picture because it doesn't in any way that we could prove immediately correspond to something in that picture. It sort of corresponds to the double sum, but then I would have to spell out exactly what that means. So AB is just, whatever A converges to, whatever B converges to, multiply them together. So what we're going to do is we're going to estimate this and see what happens. So let's continue here. So the modulus rather, of this partial summation of Cn minus AB, well, we're going to estimate that. All right, let's see if we can get a handle on this term. What we're going to do is we're going to approximate it by, this by An times B. So we're going to add and subtract An times B because that will allow us to split it into two more convenient terms. So we're going to take this Cn term, we're going to subtract A sub cap n times B, and then add A sub cap n times B. And then, of course, we'll have minus AB. So we're going to do that. And then, of course, immediately, what does that lead to? The triangle inequality. So the first term will be the summation Cn from 0 to cap n. And then we'll be subtracting from that A sub cap n times B. And then we'll get another term here, which a B factors out, and we get A sub cap n minus A times modulus B. Now this term I'm really not worried about. We're going to bound that by epsilon over 3 or 4, and then we'll deal with that. This term is easy to manage because I can produce, for large enough values of cap n, I can be guaranteed that this difference is going to be less than any positive number I want because I know that An converges to A. So this term is really nothing to worry about, although we do have to manage it. This term is really where it's at here. So in order to understand this term, notice that An is a sum I equals 0 to n of AI, and Cn also kind of has that summation in it as well, because Cn is the sum of all of these terms in red, which can be organized as a bunch of terms like A1 times something and A2 times something and A3 times something. So what we're going to do is we're going to reorganize this finite sum Cn. Because it's finite, we don't need to worry about the validity of the reorganization. And then we're going to compare it to this summation of AI, which is here, An. So let's do that. So this is the summation I equals 0 to cap n of A sub I times. Now, A sub I doesn't, in this summation of the CNs, doesn't multiply all the values b0 through bn. It only multiplies b0 through bn minus I. And so here, what this multiplies is the summation j equals 0 to cap n minus I of b sub j. So basically what I'm doing is I'm taking this red part and I'm splitting it into columns here. So there's one column, and then there's the next column, and there's the next column. And the height of that, each column corresponds to this inner sum, and each one is multiplied by AI, because AI is the constant that multiplies all of these different b sub j's. So that is, that opens up this summation of the CNs there. Now let's open up this summation of AN, and we'll see that something interesting happens. So this is minus the summation I equals 0 to cap n of AI times, so that's for the AN, and then times B. And it doesn't matter whether I times B on the inside of the sum or the outside of the sum, so I'm not going to parenthesize it at all. So that opens up what this thing is doing. And notice we've got a summation on I and a summation on I of AI, and so these things are going to combine soon. And then this thing, I'm just going to write plus epsilon over 3 for n greater than, say, n1, because an converges to A. So you know what I mean, like it just force this thing to be less than epsilon over 3 times the modulus of B, and then you'll end up with an epsilon over 3 here. So I'm not going to belabor that point. So now we have this thing to manage, and you can tell that I've chosen epsilon over 3 here, so this is probably going to be split again into 2 portions. So let's expand this and see what happens to this. I'm going to merge the sums, and then I'm going to apply triangle inequality to the sums, but let's not get ahead of ourselves. So this is the summation of AI from 0 to cap n of AI times, well, what is this thing? This thing is actually one of the partial sums of the B series, but it isn't B sub n because it goes only up to cap n sub I. But it is a partial sum. It's B sub n minus I. And then this is minus B. So basically, I can bring these two sums together, factor out the AI that's multiplying everything, and I end up with a sum of this form. And then I get, of course, plus my epsilon over 3. This thing is now a finite sum, and it can be split by the triangle inequality. And this epsilon over 3 is going to get annoying, but I don't have much choice at this point. So let's split this thing by the triangle inequality. And that's going to allow us to move the modulus signs inside. So we're going to get the summation of modulus AI times modulus B and minus I minus B. And then that's the summation I equals 0 to n. And that's plus epsilon over 3. Now here's where things get a little bit dicey. So what does this really represent? Basically, this is the error in the estimation of Cn, the summation of the Cn's from n equals 0 to n compared to the product AB. And each of these represents an AI times the difference between a Bn minus I and a B, which basically represents the complement of these red columns. The Bn minus 1 minus B is essentially, that's no good, that's essentially giving us this structure here, right? The entire remaining infinite sum, and it's being multiplied by modulus AI. So this entire infinite sum, this tail sum, is multiplied by A1, and this sum is multiplied by A2, and this sum is multiplied by A3, and everything has a modulus. So Remember, we're trying to show that this thing has a limit of this. And so we're actually trying to control everything here to be small. We've taken the difference already between the thing we want and the limit we want it to be equal to. And so everything has to be controlled to be small. The only easy term has effectively gone away. It's epsilon over 3. But now we need this term to be small. Now let's talk about why that term is small. So I can give you 2 reasons why that term is small, and that's actually sounds like good news, but it's bad news. Reason number 1 why that term is small. Well, if this subscript, cap n minus I, is a big number, so that is like these cases here, if cap n minus I is a big number, then we've actually added up many, many terms of the sequence B before subtracting the limit. And so the tail terms are going to make some very small amount, right? Because we know that the series converges to B, right? We're assuming that the series Bn converges to B. So if we just take the remainder after calculating many, many terms, then that will already be very close to B. So if the subscript cap n minus I is a big number, then this thing will be small. There's no reason to believe in that case that AI would be a small number, because in that case, I is probably a small number, right? If this is going to be a large number, then I is going to be a small number, and we're looking at like A1. There's no particular reason to believe that A1 itself in an infinite series is a small number, right? I mean, whatever, the early terms can be whatever they want, and it can still converge. So this will be small when the subscript cap n minus I is a really big number, but in that case, this won't be small. But that's okay, because this thing will be responsible for being small, right? Now, okay, so basically we're making the argument that this thing has to be controlled to be constant or bounded by constants, say, maybe just bounded. And then this thing will be small because this subscript is really large. And that's true if that subscript is really large. But some of the terms that appear in this sum, this subscript is not large at all. When I is very close to n, then this subscript is like B1 or B0. And those are nowhere near B because we haven't had that convergence yet. So now we're looking at these things over here, right? This one and this one. In these cases, B sub 1 and B sub 2, there's really no reason to expect them to be very close to B because we haven't had a chance to converge yet. And so this is going to be big. But then the AIs are presumably going to be small because they are the later terms in a series that converges to a value. And so we hope to control these things to be small in that case. So what's confusing about this is we seem to have 2 different but contradictory reasons why we hope this whole thing would be small. Some of these terms are small because the subscript on B is really large. And some of these terms are small because the subscript on A is really large. And none of the terms, I mean, arguably none of the terms have both of those going on. So what are we going to do? Well, we're going to have to split the sum. We're going to split the sum into the early part and the later part. We're going to try to figure out later which part is the early part and which part is the later part. We're going to split the sum into the first part of the sum and the latter part of the sum, and then we're going to try to control each of them very carefully. So let's split this into the summation I equals 0 to cap m for some m, and I know I haven't introduced cap m into this proof yet, but it'll come. So like later I'll decide the value of cap m, okay? So just take for granted now that this, whatever it is, this argument applies to any cap m between 0 and cap n. So we're going to split this sum into this portion of the sum, b sub n minus I minus b. And then we're going to get the latter part of the sum, I equals 0 to cap m minus, no, plus, no, I did that completely wrong. From cap m plus 1 to the last term, which is supposed to be n. So I'm just taking this finite sum and I'm splitting it into 2 portions, and I'm getting the sum of each portion, minus b. So, and then my annoying epsilon over 3 out here. Okay. So now we have 2 portions to manage, and we're going to have to manage each portion carefully. So this portion we're going to control to be small on the grounds that that I is large, and therefore this might be a small number, but this is going to be large indices for A. And so the large indices for A are going to give us that these things are going to be small. This one we're going to control because I is small, and so these are going to be large indices on the B. So how do we make this happen? First, notice that the sequence Bn converges to B. And so the terms Bn minus I minus B converge to 0. Now, if these terms converge to 0, then they are at least bounded. And so we're going to choose a bound. So Bn minus I minus B, well, let's just say generally Bn minus B, this sequence converges to 0. So it's bounded. And so we're just going to choose one uniform bound for all of these. So choose K, bounding the modulus of B sub n minus I minus B for all possible values of n and I. So that allows us to replace this with a K. Now, is that useful? Well, we'll see. So if this is a K, then this is simply K times this summation. Now, this is a summation of the moduli of the terms AI. What can we do with that? It's a summation from m plus 1 to n, which is actually a difference between two partial sums, right? This is the partial sum that ends at stage n minus the partial sum that ends at stage am. But it's not the partial sums for the sequence AI, it's the partial sums for the sequence modulus AI. So these are, so once we convert this to a K, we are basically looking at the difference between two partial sums of a sequence of the moduli of AI. So who cares? Well, we have an assumption about AI. We assume that AI is an absolutely convergent series. And so those partial sums form a convergent series. So once this is bounded by K, so notice that the summation I equals m plus 1 to n of the absolute value of AI times B sub n minus I minus B is going to be less than or equal to K times the summation I equals 0 to n of absolute AI minus summation I equals 0 to m of absolute AI, the difference between two partial sums which approximate the summation of the modulus of the AI. Why am I making it look like the difference between two partial sums? Because the sequence of partial sums converges. So the sequence of partial sums of the infinite series AI absolute or AI modulus converges. And if it converges, then it's Cauchy. And so who cares if it's Cauchy? Well, then we can choose a value m, and we can take for granted that beyond that value, any two partial sums are going to differ by at most, well, whatever positive number we want. And so what we're going to do here is we're going to invoke the Cauchy property on the sequence of partial sums for this absolutely convergent series in order to say that there is some value of m, beyond which the difference between any two terms will actually be as small as we want. Now, how small do we want it? We want it small enough that I'll cancel the k and end up with an epsilon over 3. So I think it's time to erase this picture, and then we'll make that happen. So what we're going to do now is we're going to choose some value that will, some m that will actually make that happen. So that's Cauchy. And so we're going to choose m so large that for all n1 and n2 greater than or equal to m, that this thing here, summation I equals 0 to n1, absolute AI, minus summation I equals 0 to n2, absolute AI. This difference is less than epsilon over 3, and I'm going to drop a k in there because I have a k to cancel. Okay? So what will that give us? That will give us total control over this term because we've chosen m large enough that we've got this term less than epsilon over 3 k times k. So that will allow us to continue with our computation, and we will get this thing is less than or equal to summation I equals 0 to m of modulus AI modulus b n minus I minus b plus epsilon over 3 plus epsilon over 3. So the first epsilon, the rightmost epsilon over 3 is the one I've been carrying for a while. And this epsilon over 3 is what results from this thing. We've bounded this at k, then we've computed this to be necessarily less than epsilon over 3. And one of the really important things that we've done here, and it will come up at the end of this proof whether the proof is valid, is that we are trying to show that this can be made small by appropriate choice of cap n. I have not actually chosen the value of cap n. I've chosen the value of m so far, and I will later choose the value of n. But that's okay because the Cauchy condition says that no matter what n is, so long as it is beyond m, this thing will remain true. So we can trust that this is true regardless of the actual value of cap n. And the choice that we've made here of m is not dependent on what the value of n would be. The reason I'm pointing this out is because when we actually do choose the value of n, we're going to choose it like after the fact to have depended on m. So I want to make sure that that dependency is not a circular dependency. So we've chosen m so that no matter what n should happen to be, this will actually work by the Cauchy condition here. So that gives us one term left to control plus an epsilon over 3 plus an epsilon over 3. Now, how on earth are we going to control this term? Well, let's figure out what's small in this term. We've dealt with these terms for which this was completely like unknown, but this one was controlled small. And now these terms, the idea here is that this is going to be virtually unknown, but these terms are going to be themselves small. So let's see if we can make that happen. So this term AI is at least bounded. So let's let L be a bound for AI, for the absolute values of AI for all of them. We know that the absolute values of the AI converge to 0, so there must be some bound. So let L bound modulus AI for all I. And then we get, this is less than or equal to L times the summation I equals 0 to m of b n minus I minus b. Now, here, the n is yet to be chosen. And so what we would like to do is we would like to make sure that we choose an n so that this thing is actually quite small. So how can we do that? Well, what we're going to do is we're going to actually try to control this term kind of independent of this. So what we're going to do is we're going to choose an n2. I've already got an n1 over there. So I'm going to choose an n2 so that for all n greater than n2, then b sub n minus b is less than something really, really small. So I'm going to take an epsilon over 3. I'm also going to divide by L because I intend to cancel this bound. And I'm also going to divide by an m because, well, I guess I have m plus 1 terms. So I'm going to divide by an m plus 1 because I intend to basically use this a whole bunch of times to bound every one of these terms. So then this thing, I forgot my epsilon over 3 in both cases. So this bound is hopefully going to suffice for this. Now there's only one thing left I need to know. I need to know that when I take b sub cap n minus I, it really will be an index of b which exceeds n2. And so what I'm finally going to do is I'm going to finally choose n greater than m plus n2. The reason for this is that this will force I. So what's going to happen here is that n minus I is going to be greater than or equal to n minus m, and n minus m is going to be greater than n2. So the significance of this is we're choosing cap n here so large that when we take cap n and subtract any I in this range, then we will still end up with an index which exceeds n2 and activates this assumption on bn minus b. So we will still have this. And then this thing is just m copies of something. Well, it's not m identical copies, but it's m plus 1 terms, each of which is bounded. And so we can apply all of those bounds simultaneously. This is m plus 1 terms, and every single term has a bound, and the bound is epsilon over 3 m plus 1. So that bounds each one of these terms basically independently, and then we have what we need here. And then don't forget the epsilon over 3 plus epsilon over 3, and everything cancels and yields an epsilon. So this demonstrates that the difference between the intended thing and the limit that we claimed can be made smaller than epsilon by appropriate choice of cap n. So logically, what's happening here is on the basis of the bound of b, we choose the value of cap m. Then we leverage that value to find some n2, and on the basis of that, we finally choose the value of cap n. And if we choose cap n so large that this becomes true, then everything here totals less than epsilon, and we have exactly what we were trying to prove. So this demonstrates that this thing does indeed converge to AB.